Hello everyone, welcome to this lecture of computer system security. We're going to continue our discussion regarding encryption algorithms. If you remember, we've talked about DES, data encryption standard. We've finished DES, and then I've started talking about triple DES or 3DES, and I talked about it. I said that triple DES is in fact 3 times repetition of DS, that of course we are applying different keys. So we get the plain text here, we apply it, we do 1 round of DS using key number 1. And then what we get here, which I showed it as text A, this is of course a ciphertext text with respect to encryption round 1, but we apply it into another DES for a decryption process, not an encryption here. And we use a different key, key 2, and then what we get here, which is supposed to be something, of course it's some type of confusion and diffusion on B with respect to A. We again do another round of encryption on B using the third key. And what we get is called our actual ciphertext. And this way I explained that we can basically increase the key space from 56 that we used to have it in basic or original DES. We increase it into 56 times 3, because of course key 1, key 2, and key 3 are going to be different values. So the key size is going to increase to 168. And we've talked about this, and I said that it's an effective way people are using it. But now I'm gonna discuss why do we get to have 3 rounds of DES, data encryption standard. Why not 2 of them? If, for example, we assume that we have 2 round of DES, DES1, let's say, of course, with key number 1, and then we get DES2, this is not going to be very effective. Of course, at the first place, we assume that we have keys and they are not different. So the first impression is that the key size should be 56 times 2, which is 112, and should be big enough. 2 to the power of 112 is big enough. So why not 2? The reason is there is a discussion that shows us there's a type of attack that we can talk about it now. It is called meet in the middle attack. In the meet in the middle attack, based on this attack, the attacker doesn't have to kind of search all the 2 to the power of 112 space. In fact, we have cascaded 2 DESs with the goal of expanding the key space to this, but we can't get that. Why? Here's the key. Look, if we apply a text like M, a plain text like M, and get a ciphertext like C, so we are assuming that okay, the attacker should have a search in all different values that key 1 and key 2 may get each other. So it's going to be 2 to the power of 56 for key 1 times 2 to the power of 56 for key 2, which is 2 to the power of 112. Yeah, this is what we expect, but the attacker doesn't have to do it because he or she can do meet in the middle. The meet in the middle says, I search in parallel all possible keys for round 1 for DS1, all possible values for key 1. So it's going to be 2 to the power of 56. And in parallel or separate, in separate of that, I do all decryptions from this side using key 2 on the ciphertext. And again, what it needs a search in the space of 2 to the power of 56. So I'll get 2 to the power of 56 values or encrypt ciphertext here at the end of the round 1, and I'll get 2 to the power of 56 different decrypted values or ciphertext here. Let's call it X1, what I get from the this side X1, and what I get from decryption X2. If X1 equals X2, what does that mean? It means that, okay, this is the right set of keys. So the meet in the middle says we find key 1 and key 2, or let's say key 1 and key 2s are correct uh, if they satisfy this equation, this equality. Encryption of M with respect to key 1 equals decryption of ciphertext with respect to key 2. If both of them get to the same value, it means that this is a right pair of key 1 and key 2. And of course, we have to do a kind of search for that covers, that spans 2 to the power of 56, but it is not 2 to the power of 112. We didn't get to the 2 to the power of 112, and which means that we basically couldn't expand the key. In terms of strength, in terms of security, double DES works similar to a normal DES. The only thing we need to do, we need to save all the values here, save all the decryptions here, and then just compare them. That comparison, if we want to be very accurate, that comparison is going to be going to add another kind of power to the another search in our key space. So overall, we can say 2 to the power of 56 plus 1 for the comparison, which is going to be 2 to the power of 57, which is again not that big. It's not super improvement with respect to 56. So that's why we say that 2 encryptions, and this is a general idea that later we see that people will use it. This idea can be used for other encryptions as well. For example, you have AES, you can do triple AESs after each other. We'll talk about it in the rest of this lecture. But what this analysis says us about the meet in the middle, it says that cascading 2 of same encryption algorithms using different keys is not gonna, of course, using different keys is not gonna expand your key, because the meet in the middle attack can happen. Okay, I'm gonna next talk about the AES, Advanced Standards Encryption. Here is a kind of short history about AES. In 1997, DES was broken. And then in 97, National Institute of Standards and Technology asked for proposal, 15 proposals submitted. And then 5 finalists in 99. Excuse me. And in 2000, NIST chose region dual, which was the name of algorithm, as the next standard that they wanted to pick. And it works with these sizes of key: 128, 192, 256, and the block size or the ciphertext size is 128. Of course, this is a block cipher. It means that it works on a block of data, not the stream of data. Okay. Here is a general architecture of the AES encryption algorithm. The 128 bits of plain text enters here, and then it's going to be XORed. This is the XOR operation. I put it in one of the slides. Let me just, for some of you that, I'm assuming that you know it, but just in case, if there is anyone who doesn't know how the XOR works, this is how XOR works. Let me just quickly go over it, and then I'll get back to that slide. Here's the XOR. If you have 2 inputs, X and Y, of course, 1 bit values in binary. XOR is a logical operation that works on the binary numbers. If you get 0 and 0, these are 1 bit 0, 1 bit 0, the XOR is gonna be 0. If you have 1, 0, 1 or 1, 0, which basically means that they are not equal, the XOR gonna be 1, and if they are both 1, the XOR gonna be 0. Of course, when we say that, for example, XOR of 2, let's say 1 byte number, 1A, and let's say, for example, 0E, when we say the XOR, it means that we need to first expand it and show it as a binary. This is a binary of 1A, and this is the binary of 0E. And then we do the XOR on the corresponding bits. So these two bits get XORed. I get 0, I get 0, 1, 0, 1, 0, 0, 0. So this is the XOR operation that I'm pretty sure that most of you know that, but I just wanted to review it before we get forward. Okay, here's, let's get back to the slide of the general architecture of AES. Here is how AES works. It gets the 128 bits of data. It just immediately XOR the data of 128 bits with the key. And of course, when we say XOR, it means that 128 bits of the plain text is going to be XORed bit by bit or bitwise with the key 0. And that's it. There is no initial permutation, final permutation. That's it. After that initial XOR, we get to the rounds. There are 10 different rounds that kind of performs the encryption. And we have, of course, again, a round key generator. Okay, the 120 bits of plain text or data is going to be considered as a matrix like this, that we call it input state or state matrix. This is byte number 1. I'm saying byte because, 16 byte times 8, it gives me 128. So this is byte 1 of the data, and this is the last byte or byte 16 of the data. And here is byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, 7, 8, all the way to byte 16. And we call this input state, or we have this matrix all over the algorithm in different rounds. We call it, when you say input state, it means here. The matrix that we see here, it is called input state. But we see that matrix here at the end of each round, and even the middle of every round. We call it state matrix. Anyway, let's get to the one of the rounds. Here is round number I, and all the rounds are similar except the last one, which is slightly different. I'm not gonna get into the details of the last round. How is that different? But most of them are, all of them following the same thing that you see here, except the last one, which is a little bit different. We see 4 different steps or 4 different kind of phases in each round, per each round. The first one is called byte substitution or SBox, which is similar to what we had in DS. There is a table, the data refers to that table. Based on the data, we go to one of the cells of that table and bring something, and that thing is going to be replaced with the data we had. So that's why people call it substitution. You substitute your byte with a different byte. We talk about the detail of substitution in AES, and then we have shift row, which is a type of permutation. It's a byte level permutation. You permute the bytes, you shift some of the rows in the, again, on the state matrix. We are talking about the state matrix, which is basically our 128 bits of data. This is your state matrix. You shift some of the rows in a way that we'll talk about it. And then we get the third phase or third step is called mixed column. It is some type of matrix multiplication that I'll talk about it, but it's defined over Galois field 2 to the power of 8 with the aim of maximizing the entropy that we'll talk about it. And the last thing, or the last step, again, is very easy. It's just a simple XOR. And here is a place that key or the round key is going to be fetched, is going to be used. The round key is used just in order to make a bitwise XOR between the round key and what we get from the mixed column step. And of course, round key is 128, and we get 128 bits of data here. That when we talk about it, we show it this way, say state matrix or input matrix. But when you want to do the actual XOR, you need to expand it and write it as a kind of 128 bits of data and XOR it with the key. And this is the XOR operation that I just done. Okay, let's see the first step, which is the S box or substitution box. Here, unlike the DES, that if you remember, we said that in DES we have 8 different S boxes. No, here we only have one S box. AES only has one S box, and that S box is pretty big. It's a 16 by 16 table. And numbers of this table are kind of defined in a way that it maximizes the entropy. And if you look, kind of adjacent numbers are very different. They have many bits in difference. So it means that if you read this, or if you read this, you'll get many bits in different. So how we refer to this S box is this. Suppose that this is our state matrix. This is our state matrix, and we want to substitute or we want to apply the S box on the EA. So S box of, sorry, it was EA. S box of EA for computing the S box of EA, the AES algorithm looks at the data. It is EA, it's composed of EA. Of course, it means that this is an 8 bits of data. One nibble, every 4 bit we call it a nibble. The high nibble and low nibble, or the high hex number and low hex number. The high number is going to be used to address columns. So we look at E, we go to column E. This is column E. This is the column E. And then we look at A, we look at the low nibble and go to the, I'm sorry, we go to row number E. The high nibble refers to the row. The high, EA, it refers to row. So we go to the row E and column A. So forget about this and column A. And of course, we find the intersection, which is here. So the value EA points to this cell. What's the content of this cell? It is 87, of course, in hex. So we substitute this value EA with 87. For example, 98, let's do one together again. 98, we go to row 9, column 8. So I get 46. So you see 98 is replaced or is substituted with 46 and so on. This is called SPOX, and you know it's very similar to what we had for DES, but here we only have one SPOX. There are not multiple SPOXes. We only have one, which is big enough, and it performs all the substitutions for us. After the SPOX step, we go to the shift row. Shift row, like I said, is a byte level permutation, and it performs a simple operation. This is again the state matrix we got. This is the state matrix. Yeah. When we apply to the shift row, every row is gonna be shifted to left some numbers. The first row is going to be shifted 0 bytes. So that's why we see S0, 0, it just appears here. S0 and 1, it appears the same place. S02 appears at the same place, and S03 appears at the same place. Row number 1, the reason I say row number 1, because normally we call it row 0, row 1, row 2, and row 3. The row number 1 is going to be shifted 1 byte to left. So it means that this S11 appears here. So that's why, see, S11 is here. This also shows that we shift 1 byte to the left. S12 appears here. You see, S13 it should appear here. That's you see. That's one. And of course, S1 and 0, it kind of wraps around and appears here in the very right side of this row. In row number 2, we do again the left shift, but this time we shift twice, or we shift 2 bytes. So S2 and 2 should appear here because we are supposed to shift 2. S2, 3 should appear here. So if you look, S2 to here, 2, 3, 2, 0, and 2, 1. And for the third row, or the last row, we do the shift, but this time we do it three shifts, or we shift every byte 3 times to left. So S33 appears here, you see, and then S2, S01 appears, and then S31 and S32. So this is the operation of the shift row. And here's again another example of state matrix, and you see that this is a kind of output of the shift row step. The first row is not changed. Second, or row 0, it doesn't have any change. Row 1, only 1 shift. Row 2, 2 byte shift, and row 3, 3 bytes of shift to left. So this is the operation that we do in the shift row step. The third thing we do in AES encryption is called mixed column. The mixed column is basically a function or a transformation that operates on every column individually. So it looks at the values of the whole column and determines the value of this cell. Again, it looks at the value of the whole column and determines the value of this cell. It looks at the value of the whole column, determines the value of this cell. Looks at the value of the whole column, determines the value of this cell. And it is basically a matrix multiplication. What it performs is this. It takes a column, let's say this column, puts it here, and now multiply it to this matrix. This is a 4 by 4 matrix. You see 2, 3, 1, 1, 1, 2, 3, 1, 1, 1, 2, 3, 3, 1, 1, 2. Which is of course something similar to the shift row. This is shifted 1 bit to right, 2 bits to right, and 3 bits to right with respect to the first one. Yeah, you get this row, you multiply to whole column. What you get is this cell. This is a matrix multiplication, I'm sure you remember it. You get the second row, you multiply to the whole column, of course, 1 by 1, corresponding this gonna be multiplied here, second one gonna be multiplied here, and so on. What you get, and you add all of them together, what you get is this cell, and so on. So that's why we say in a mixed column, all values of a column, of a specific column, are going to contribute in order to determine the value of one of the cells of that column. For the second cell of that column, again, all values of that column is going to contribute, of course, with different weights. There are going to be different weights on each, but the same thing. For the third one, all values in this column are going to be red, are going to be contribute in order to determine the value of that column. And this way, we do the mixed column. And the last thing is key, add round key. It's called add round key, which is very easy. Which is very easy. In add round key, what we get is we just XOR the state matrix. This is a state matrix, and here is the key. Of course, the round key. When I say key, I mean the round key. We XOR them, XOR every corresponding bit. If I want to show it in a different way, this is the state matrix from bit number 1 to bit number 128. We get the same thing for the key for the round key, bit number 1, number 128, and we XOR them bit by bit, and based on the operations of XOR that I just explained to you. And we get something out of that, which is called the output of the add round key. And the reason they call it add round key is that sometimes the addition operation in module, if the addition modulation, let me put it this way, if the addition operation is defined in modulo 2, in modulo 2, addition, the operation of addition or summation equals the operation of XOR. That's why they call it add round key. We are in fact adding, or we are summing the key up to the state matrix, but of course we are doing it modulo 2, in base 2. If we do it that way, that's why they call it, we do XOR, but they call it add round key. The reason comes from the name comes from that reason. Okay, we are done with two encryption algorithms, DES and AES. And what I'm going to do next for you is that I will, you will see an assignment that you are supposed to calculate one round of DES. For AES, I'm not going to ask you the same thing because one of them is enough, but I'll provide you an extra resource, an additional resource that gives you an example how the AES encryption algorithm works on an example binary plain text and key, and you can follow that, but the idea is the same. I explain you the idea, and of course, if you know the AES well, if you dive into the details of that, AES is going to be the same. Of course, the algorithm is different, but in terms of doing it manually, I don't think we need to do it another example in a manual. You can just, there should be enough learning from doing the DES manually. Okay, we are done with two encryption algorithms, AES and DES and AES. We will be talking about another encryption algorithm, RSA, but before that, I'm going to talk about a different concept, which is very important when we talk about encryption algorithms. That's called encryption mode. Okay, the encryption mode basically answer an important question, and that question somehow refers to block cipher or block encryptors. If you remember, when we defined block cipher, we said that block cipher, they take inputs which are both plain text and key in a fixed length, let's say B bits. Sometimes key is different, might be less or more, but in some of them key is also B bits, and the output is also going to be generated most of the time the same number of bits, B bits. So the one big question is this: how about if I have a situation, or if I have a data which is longer than B bits? For example, in AES, we said that plain text should be 128 bits. How about if I'm gonna encrypt a file which is 1 kilobyte? What should I do then? So, okay, the simple answer to that, or the easy answer to that, is to break the plain text into blocks of B bits and encrypt them or cipher them. But there are details here, or there are different alternative approaches here that can be used in order to encrypt blocks of the data which are somehow related to each other. So if let's say I have 10 blocks of the data which all belong to the same data, and I'm gonna encrypt them. If I do something easy, eventually we'll see that the actual security that I get might be compromised. Okay, there are 5 types of encryption modes kind of approved, or let's say listed by NIST, that we are going to talk about them in terms of how they work, and also we analyze them in terms of security. The first, okay, this is a formal definition. A mode of operation or a mode of encryption is a technique for enhancing the effect of the cryptographic algorithm and adopting the algorithm for an application that has sequence of data blocks or a stream of data blocks. So if you have multiple blocks, or if you have a stream of data that comes and you want to still use a block cipher, what you are going to do. And of course, they are applicable to symmetric block ciphers like DES and AES. Okay, these are this is the list of the the 5 encryption modes or operation modes. The first one is called ECB, or electronic code book, and we'll talk about it. This is actually the easiest in terms of implementation, in terms of complication. It's the simplest one, but at the same time, we see that it has the lowest security. It's not that great. And also we have cipher block chaining, that we somehow chain different block or consecutive blocks, which is better in terms of security, a little bit more complicated. We have cipher feedback, we have output feedback, and we have counter mode, that we'll be talking about them in details, and we analyze them in terms of security. Okay, let's get started with the first one, electronic codebook or ECB mode. And of course, when we say ECB mode, it means that you can run DES in ECB mode, you can run AES in ECB mode, you can run RSA in ECB mode. Any block cipher, any block encryption algorithm can be run in ECB. What it says is this: it says you have a n number of blocks that all belong to your data. And of course, for example, they are, let's say, 1,280 bits. So of course, your AES doesn't support this width. You break them into 128. So this is going to be your block number 1, block number 2, and block number 10. And you want to encrypt them using a key. So the ECB mode says, okay, get your data. The first block is going to be encrypted with the key, and you get the cipher 1. So P1 is block 1, you encrypt it and you get C1. P2 is block 2, you encrypt it with the same key. This is the same key with respect to what P1 is encrypted, and you get the encrypted version of that C2. All the way until the last block, which is here in our example, the block number 10, you encrypt it using the same key, and then you get the ciphertext number 10, and that's it. You now concat them, put them together. This is 1,280 bits encrypted version of your input data. So this is called ECB mode. And when it comes to decryption, the same thing. You break the ciphertext into blocks of 128, and every 128 is going to be decrypted separately. As you see, there is no relation between the blocks, between the adjacent blocks in terms of encryption and decryption. Every block is going to be treated separately, as a separate, as a kind of separate entity. We encrypt it separately, we decrypt it separately. The only thing which is common between different blocks is that they're all using the same key. All the 10 blocks or n blocks, whatever number are, they're gonna be encrypted using the same key. Also in decryption kind of phase, all the n different blocks are gonna be decrypted with the same key. So this is called electronic code book. And here is a kind of math representation of that. We say that the ciphertext of block J comes from encrypting plain text block J and the key. And J ranges from 1 to n. For example, if n is 10 and we are talking about AES, we are in fact encrypting 1,280 bits. And this is the decryption part. And like I said, the main feature is that the same key is gonna be used for encrypting all the bits, sorry, all the blocks of the plain text. Okay, we'll talk about it, and we show the kind of shortcoming and weaknesses of this. And later we get this conclusion. This is a kind of important conclusion, that because of the weaknesses or shortcomings that ECB mode has, uh, it is not recommended to be used for blocks of data wider than what your encryption algorithm support. It means that if you want to encrypt something which is bigger than, for example, 128 using AES, it's better not to use ECB. So use something else. Okay, and here are the kind of some of the weaknesses. First, block substitution. Block substitution can be done. For example, if you have a block of 1,280 bits, I can get the second block. I can just cut it or copy it and use it in a totally different text of 120 or even more. Let's say 496 bits of data. Whatever. I use it, and I can just use it as a block here, and no one understands it, because this this block is it doesn't have any relation with the previous block or the next block. So I can, and I'm sure that it is being encrypted with the key. So probably I can use it in a different ciphertext without anyone be kind of alerted by that. Of course, this is a fast and simple method. And like I said, blocks are going to be encrypted independently. And again, here is a problem which is restated here, that the block can be copied from one message and can be pasted or can be used in a different message without possibly detection. And there is no error propagation. I'll talk about the error propagation to say what exactly we mean by error propagation. But before that, I'm going to show you some real examples, real data which are being encrypted using ECB mode. And like I said, overall, it's not recommended for the messages which are longer than the size of the cipher. Okay, look at these two figures. This is the original data that we have. Of course, this is going to be bigger than 128 bits. This is a figure, let's say 300 by 400 grayscale. If we say each pixel has 8 bits minimum, it's going to be this number, 300 times 400 times 8 bits, which of course is way bigger than 128. So they break blocks of 128, let's say something like this, and then they applied AES in the ECB mode. And if you put the encrypted data next to each other and just represent it as an image, because that's going to be again the same size of data after encryption. After you encrypt it, you'll get the exact same size of it. If you use the encrypted data as a values for pixel, you see something like this. And it is very clear that although the AES itself is strong in terms of offering both confusion and diffusion for 128, it means that every 128 is statistically is encrypted in a way that it is statistically independent of the input or the diffusion property we see. But if you put together all these blocks next to each other, because since there is no relation in the encryption of these blocks, and they are going to be done independently, they carry the high-level features of the initial data. So the patterns that you see here, they're easily detectable here. Basically, we have done nothing. We just it just seems that we've done some basic filtering on the image. So we wanted to no one be able to understand the meaning of this data, or in this case, the meaning of this image, but it is very kind of simple and obvious that everyone can realize what the actual data is. Here is another example, which is again another image, which is a big size data. The reason I use images is that they can be visually interpreted, and we can visually see that the AES, which is pretty strong encryption algorithm, when it works in the ECB mode, it is not able to visually hide the kind of plain data. The encrypted data is highly correlated to the input data. So, which means the weakness of the ECB mode. Okay, let's define some features that we expect to see from different modes. Of course, we don't want to work with the ECB mode. ECB is very simple and not efficient. But how should we build more efficient or better modes of encryption to encrypt larger portions of data, blocks which are wider than or bigger than the block that our algorithm accepts? There are some criteria that I'm going to talk about them. The first thing, of course, is overhead. Of course, we want to improve the security, but at the same time, we also care about the overhead. It means that how many additional operations we need to do for encryption and decryption. This is important thing. This is a very important thing. Of course, we have the encryption algorithm, which by itself requires some computations. For example, in AES we just talked, we need SBox. For the XBox, you need to refer to memory, bring some data, do substitution. Then we have shift rows, we have mixed column, we have add round key. All of them, they need computation. So I have already committed to do some computations, but for working mode, for the mode of operation, you are imposing me more operations. So I don't want to get, I don't want to kind of end up having to run another series of computations which are as big as or as heavy as the base encryption algorithm. The second thing is diffusion. This is what we don't see in the images that I showed you. How the plain text and ciphertext are statistically related or are independent or dependent or independent. Of course, we want to see the plain text. Of course, when we say plain text here, we are talking about big plain text. We are not talking about one block of data. The whole blocks that we get, let's say 10 blocks of data that we have, how the 10 blocks of plain data is related statistically to the 10 blocks of cipher data. They should show a good independence. There should be a statistical independence between them. And something like ECB that we just talked about, it shows a very low entropy. Low entropy means that they're correlated. There are relation between them, and we can predict the data. Low entropy kind of equals to predictability or lack of randomness. When it comes to encryption algorithms, the more randomness, the better, because the attacker cannot guess that. And of course, security. We don't want to have any leak of information from ciphertext. This is another property that we consider while developing operation modes. And the two others are error propagation and error recovery. Error propagation says, look, you have encrypted something, you provided me 10 blocks of cipher data. Let's say this is block 1 to block 10, and this is a cipher data. Yeah, this is the ciphertext. and I'm going to save it somewhere, or I'm going to transfer it somewhere. Some bits of 1 or 2 blocks may go wrong because of the transfer, because of the, for example, media that I'm using. It might be a wireless media, or it might be wire, but it's next to some uh, high voltages, or it's next to some situation that the data just while being transferred got affected, and one of the bits in the cipher data is now wrong. Of course, if you want to decrypt this, uh, some blocks or this specific block cannot be decrypted properly because one bit is now wrong here. So the error propagation says this kind of points to the property that an error in the JACE block impact JACE block and all subsequent blocks in the plain text. So if this is the block number 5 and I'm decrypting this, in the decryption process, of course, block number 1 can be decrypted properly because block number 1 is okay. Block number 2 can be decrypted properly. When it comes to block number 1 cannot be decrypted properly. Block number 1, we fail decrypting block number 1 because of that error. And you know we have that diffusion property. If you change one bit, many things will change. So what you get as block number 5 plain text is going to be garbage. This is not basically many, but this error may propagate to other blocks as well. Block number 6 also we may not be able to decrypt block number 6, 7, and all the way to block number 10. If this happens, we say that the mode of operation, it propagates error. If this doesn't happen, it means that only block number 5 is the block that we cannot decrypt it, but the next blocks we can decrypt it. In that case, we say that mode of operation or encryption mode, it has the feature of error recovery. It means that one bit goes wrong and only one of the blocks we will not be able to later decrypt it. But blocks after that block, for example, block 6, 7, 8, 9, 10, we are able to decrypt them. This property is called error recovery. It says that the error in the JACE block of ciphertext, in fact, only one, or let's say a few. When I explained, I said one, only block number 5 cannot be decrypted. It might be few of them, 5, 6, and 7, and then anything after 7 can be decrypted successfully. If we hold this feature, if the operation mode that we define or we have created satisfy this feature, we say that it has the error recovery property. If it doesn't have, we say that it has the error propagation property. It might be a little bit not easy for you to imagine what I'm talking about now about error propagation and error recovery. We need to look at the examples, and then we realize how it works and what does that mean. Okay, let's get to the first one after ECB. I'm going to talk about cipher block chaining, or CBC. In the cipher block chaining, this figure basically shows it in a very easy and understandable way. It says of course, these are our blocks. It is named here as P1 to Pn, but this is in fact our block number 1 to block number n. So you get your block number 1, you encrypt it using the key, and then you get the ciphertext. This is a ciphertext number 1, which is the encrypted version of block number 1. When you are encrypting block number 2, before actual encryption, you XOR it with the ciphertext 1. So here we are somehow chaining the block number 2, or we are making block number 2 somehow dependent on ciphertext of block number 1. So we first XOR P2 with C1, and then we start encrypting what we get here using the key. Again, for the next block, P3, we first XOR it with C2, and then we start encryption and so on. So you may ask, what we are going to use for the first block, very first block? We use something that we call it initial vector. Okay, here's a kind of math representation of that. For every block J, we encrypt it using the key. Sorry, this is this ECB, what we talk. We say every cipher J or every block J equals encryption of plain text J and key. But here in CBC, we say every cipher J is the encryption of the PJ, which is the plain text of that block, XOR the cipher of the previous block and the key. And if we want to decrypt it, here is the decryption. Let's get back to decryption. You see, when we want to decrypt, we first decrypt the first block. What we get after decryption, we XOR it with initialization vector. And then this is going to be, after decryption, is going to be XORed with the output of the decryption. And here is your plain text. So this is the cipher blockchaining mode. Of course, we are using all of these are AES or DES, whatever. We are now just talking about how to cascade them in order to expand our AES to, for example, 1028, 280 bits. We are just coming up with an architecture of cascading, and that in that architecture, you see that how we are chaining different blocks, and this chaining is good. We'll talk about it. Okay, here is the math representation of the encryption and decryption. And here we have initialization vector that I'll talk about it. Okay, here are the properties. Some of them I mentioned. It repeats the input block to produce different cipher blocks. And yeah, okay. Every encrypting the same plain text. Okay, this is the first important property that we get, which is the impact of the initialization vector. If we use the same plain text, I'm talking about the long data, 1280 bits of data. If we get it and we encrypt it 2 different times with different initialization vectors, we get 2 different cipher text. We get 2 different kind of cipher data of 1280. The cipher 1 and cipher 2 will not be the same. Why? Because the initialization vectors we use are not the same. But this is not the case for EBC. Sorry, in ECB. In ECB, if you get a block of 1280 and encrypt it n times, all n times you'll get the same thing. But here is not the same. If I repeat it, I just need to change the initialization vector, and changing the initialization vector will change the final outcome. Yeah, and if we somehow look at the chaining, we are basically making this relation that the ciphertext CJ is indirectly related to all plain text between, before that plain text. So CJ is in fact a function of, let me put it this way, CJ is a function of plain text J and plain text 1 block before, J minus 1, plain text 2 blocks before, and all the way to the first block of plain text, which is very good. We are making a great dependency between the blocks. Yeah, and for proper decryption of the CJ block of ciphertext J, we only need a ciphertext J minus 1. We don't even need the CJ minus 1 to be decrypted or anything. So decryption is very easy. It is very kind of strong and good, but at the same time, decryption is very simple and easy. For decrypting CJ, we only need CJ minus 1, which is encrypted version. We even don't need to. Yeah, let look at here. For decrypting this block, decryption can be done kind of in parallel. You even don't need anything from any other block to be decrypted. You can start decrypting this, and at the end, you just XOR it with CJ minus 1 or CN minus 1, which is good. Okay, now let's talk about the error propagation. Okay, the error in terms of error propagation, 1-bit error in the ciphertext CJ has effect on the jth and J+1 blocks of plaintext. If something goes wrong here, only at this, let's say 1 bit of this goes wrong because of the transmission error or something. Of course, when I decrypt this, P2 is not going to be useful. P2 going to be garbage because of the diffusion properties. You change 1 bit, many bits here is going to be different. And of course, you use this C2 and XOR it. Let's say this is C2 and here is C3. You XOR it with the decrypted version of your C3. 1 bit here is error. 1 bit here in P3 is going to be wrong. And that's it. So in terms of error propagation, it doesn't have a kind of such a kind of disaster. Of course, one of the blocks you cannot decrypt it properly. That's acceptable, and only 1 bit in the block after that, in the preceding block, is going to be wrong. Other bits of that block are okay, and nothing will happen to blocks after C4, C5, and blah blah. So if CJ has error in one of the bits or multiple bits, let's say 1 bit, you will have that block. You will not be able to decrypt that block successfully. And whatever number of bit errors you have, the same number of bit errors you'll get in the block after that block. Okay, and now the last thing I'm going to talk about it, and then we finish, is the initialization vector. Please use this as the attendance code for today's class, all uppercase. Okay, the initialization vector, you may assume that the initialization vector needs to be secret. No, we don't need to keep the initialization vector secret. The only thing we just need to keep its integrity. It means that we just want to make sure that no one can change it. Because the initialization vector is going to be used only for the encryption of the first block and for the decryption of the first block. If I make sure that no one can change the initialization vector, that's okay. This is my initialization vector, let's say. Of course, it should be 128 bits, but assume that this. If I have the chance to just protect this, no one can change it, I'm okay. I can even clearly say to everyone, publicly say to everyone that this is the initialization vector. And no one can use it because they don't have the key. So it's not secret. And I will use the same thing. Of course, if someone has the chance to come and change this 0, make it 1, I'm going to be in trouble because I cannot decrypt the first block. So the only thing that we need is to make sure that the integrity of the initialization vector is attained and the initialization vector is not changed after the decryption. Yeah, and one solution is this: we can send the initialization vector, or we can store it using some ECB. In that way, because the initialization vector shouldn't be that big, we can store it using um, some kind of ECB encryption mode, so that we make sure that initialization vector is safe. Okay, I think that should be enough for today. We continue on other encryption modes, other modes of encryption from the next lecture. Thank you for making today and have a good day. Bye-bye.